Hello everyone, I'll be explaining on the topic center of a group. Center of a group consists of all those elements of the group G which commutes every element of the group. It is denoted by Zg and is defined as Zg equal to set of Z belongs to G such that Zx equal to Xz for all X belongs to G. If E is the identity element of the group, then Ex equal to Xe. Here E belongs to the center of a group. Now let us prove that center of a group is a subgroup of a group. So to prove this, let us see the condition for a subgroup. The condition for a subgroup is that if Z1, Z2 belongs to the center, then Z1, Z2 inverse belongs to the center. If these two conditions are satisfied, then we can say that the center of a group is a subgroup of a group. So let us take Z1, Z2 are arbitrary elements of Z. By the definition, we can write Z1x equal to x Z1. Similarly, Z2x equal to x Z2. Let us take equation 1 and equation 2. Now, the next step is we will multiply Z1 Z2 inverse to equation 2, because we want to find that Z2 inverse belongs to the center. So when we multiply Z2 inverse to equation 2, we see that we using associative law, we can write Z2 inverse and Z2 together. Similarly, on the right hand side, we can write like this. This will give us identity, and this similarly right hand side will get identity, and multiplying with identity will give us the same thing, so we get this. So from the definition, this implies that Z2 inverse belongs to the center. Now we got this one. So the next step is we will find Z1 operation with Z2 inverse belongs to the center. So we will take this x Z1 Z2 inverse. We can further write this as like this by using associative property. We can write like this. By rearranging, we will get Z1 Z2 inverse x. So we see that Z1 operation with Z2 inverse belongs to the center. So we can say, therefore, a center of a group is. Now we will find a simple problem, that is to find the center of a group in Q8 group, which is given by 1 minus 1 I minus I, j minus j, k minus k. To find the center of the group, we will use commutative property and check whether the individual elements present here commute each other or not. So first we will check 1. So 1x equal to x1. So for all x belongs to Q, which means x can be any value of the element in the given Q8 group. So if x is replaced by, say, minus 1, 1, which will give us minus 1 equal to minus 1, which clearly says that minus 1 1 belongs to the center of a group. Now similarly, we will check minus 1. So x minus 1. If here x replaced by, let's say, I, then this will give us I minus I minus I. Then we can see that minus 1 also belongs to the center of a group. Center of a group. Q8 group. Now we will check whether I belongs to the center. So here I, X, X, I. Here I, if X is replaced by say J, J, I. Now IJ will give us positive K, where JI will give us negative K. Now we see that I does not belong to the center. Similarly, if we check for K, for minus I, J minus K and or K plus K, we will see that they does not commute each other. So the only values belong to the center, or the only element present in the center of a group are 1 and minus 1. Now the next question is to find the center of a V4 whose elements are given by E, A, P, A, P. This is a similar question that we have done just now. That is to find the center. So here we will find whether element present here commute each other or not. So we will find individually. Let's take E. E belongs to V4. So E identity will give us E, and E with A equal to A with E will give us A only. E with P or P with E will give us P. E AP or APA E will give us AP. So E belongs to the center of V4 as they commute each other. E commute with every element present in the set. So we can say that E belongs to the center of V4. Similarly, we will check whether A belongs to the center. So A belongs to V4. E operation with E will give us A, or E with A will give us A. A into A will give us E. AB or BA will give us AB. A into AB will give us B, or AP into A will give us B. Since A square is identity, so A belongs to the center of V4. Similarly, B will find P. P into E or E into P will give us P. PA or AB will give us AB. P into P or P into P is identity. P into AP or AP into P will give us A, since B square is identity. So P belongs to the center of V4. Now the next is AP belongs to V4. AB with identity will give us, or E with identity with AP will give us AP only. AB with A or A with AP is equal to P. AP with P or B with AB is A, since B square is identity. AP and AP or AP and B will give us identity, since here AB square is identity. So AB belongs to the center of V4. So the elements present in the center of V4 are E, A, P, A. Now the next topic is cosets or cosets of a subgroup. Coset is a subset of a mathematical group that consists of all the products obtained by multiplying either on the right or left of a fixed element of a group by each of the elements of a given subgroup. There are two types of cosets, that is right cosets and left coset. We will try to understand its definition. So we will let us consider G be a group and H be a subgroup of G, and A belongs to G. Then the set H, A, equal to HA such that H belongs to H is called the right coset of H in G generated by A. Similarly, the set AH equal to a set of AH such that H belongs to the H is called the left cosets of H in G generated by A. Now if E is the identity element, then HE equal to H is equal to E is equal to H. Therefore, H is itself is a right coset as well as the left cosets. Now let us verify the properties of cosets using an example. This is a multiplicative group of G given by 1 minus 1 I minus I and H 1 and minus 1. So with this we will find cosets, right coset and left coset. So we will find the right coset. H into 1. Since it is a right coset, we will multiply it to right side. So H into 1 will give us 1 minus 1. And H into minus 1, we will get minus 1, 1. So similarly, H into I, we will get I minus I. And H into minus I, we will get minus I. Similarly, let us find the left coset, which is given by, now this is a left coset, so we will multiply to the left side. So we will get this result. Now using this result, we will verify some properties of cosets. So the first property is HE equal to EH is H, or HE is equal to H, and AEH is equal to H. So we will verify this property using the solution of left and right cosets. Since this is a left coset, a right coset, this one is a left coset, so we will see the right coset first. The right coset, so we will take this one. So this is a right coset. H into 1 is giving us 1 in minus 1, so which is equal to H. So H is 1 and minus 1, where H into 1 is also giving us H. So it is satisfying the property, this one. Now the second part is E into H is H. So we will look into the left coset since it is a left coset. So E into H is giving us H, should get H. So E into H will give us this one, which is H, because H contains 1 and minus 1, which is satisfying. So the first property is satisfied. Now the second property is H with small h is equal to H if and only if H belongs to this H subgroup. So since this is a right coset, we will look into a solution of right coset. So let's say this one H into, if we consider this as H, then we can see that this is giving us H, and the property is saying that if and only if this H belongs to H. So we can see that this one belongs to the H, so which is satisfied. So the second property is also satisfied. Now the third property is HA equal to HP. We will show this one using since both are right cosets, so we will look into right cosets. HA into HP, HA is equal to HP, so we will see that HA, let's say this is HA and this is HP, So this is giving us h, and this is also giving us h. So which means this h a is equal to hp, or h1 and h minus 1 is equal. They are equal. So we can see that this is satisfying. So this property is also satisfied. This is just a verification. You can see the proof later. There is a proof of each properties. So but I'm just showing you. So the next property is A belongs to HA. So since HA is a right coset, so we will see the right coset solution. So HA belongs to HA. So this A and this is A. This A must belongs to the solution of this one. So let's say this h into 1 is, this 1 belongs to, this is the result. H into 1 is giving us this result, and this 1 belongs to h, so which is satisfying. Similarly, 1 h into minus 1 is giving us this result, and which a contains in the h. So we can see that this property is also satisfied. Now the last property is, we will see the order of a right coset. This is a right coset and this is a left coset. So the order of right coset and the left coset is equal to h. Whether this is verified or not, we will see. So we will find the right coset first. The order of right cosets. So let us find the order of right cosets. This is a right coset. So this is a right coset. So h into 1 is giving us 1 minus 1, which is the same order of h. So we can say that this order of a right coset is equal to h, the order of h. So which is satisfying. Now the next one is the order of left coset is equal to order of h. So we will see whether it is true or not. So this is a left coset. So the order of left coset is this one, whether it is equal to h or not. So the order of left coset is 1 and minus 1, and let us see the order of h. So the order of h is also 1 and minus 1, so which is true, which is correct. So this property is also satisfied. Now the next question is, let G be a group given by minus 3, minus 2, minus 1, 0, 1, 2, 3, and so on, and H be a subgroup given by minus 9, minus 6, minus 6, minus 3, 0, 3, 6, 9. Then find the left coset and right coset. The question is very simple. We are just asked to find the left coset and right coset. Now here we will use the addition as the operator. Now let us find the right cosets. If we add 0 to the h, since we are finding right coset, we will add to the right side. So if we add 0 to h, then we will get the same thing. And if we add 1 to the h, then minus 9 plus 1 will give us minus 8. Minus 6 plus 1 will give us 5. Minus 3 plus 1 will give us minus 2. 0 plus 1 is 1. 3 plus 1 is 4. 6 plus 1 is 7. 9 plus 1 is 10. So similarly, h plus 2 will give us this, and h plus 3 will get this, and for h plus 4 we will get, and so on. as we know that right coset and left coset are same, we will get the same answer. So I'm not showing the left cosets since they are same. And if we are asked to find the distinct cosets of both right coset and left coset, then we can see that h plus 0 is distinct, and h plus 1 is distinct, and h plus 2 is distinct. These three are distinct. So we h plus 1, h plus 2 are the distinct right cosets. Similarly, since they are same, since left coset and right coset are same, so h and 1 plus h, since this is a left coset, so h 1 plus h, 2 plus h are three distinct left cosets. Now the next question is find all the distinct left cosets of subgroup H given by I 1 2 3 1 3 2 in the group S3. So here S3 group is not given, so we can write S3 group can be written as I 1 2 1 3 2 3 1 2 3 1 3 2. S3 contains 6 elements, 1 2 3 4 5 6. So yes, so we will find the left cosets. So we will start with since it is a left coset, so we will multiply to left side to h. So h will give us h, because here I is the identity. Now the next is 1 2 will multiply to h, then we will get 1 2 multiply to h, then 1 2 with I is 1 2, 1 2 with 2 3 is 1 2 with 2 3 is this, 1 2 with 1 3 2. So we will multiply these two permutations. So I'll show you how to multiply this. Since it is a 1 2 3 sequence, we will write first 1 2 3. So we will find this one using cycle notation. We can write 1 is going to 2, so here 1 is going to 2 we can write, and 2 is going to 1, so we can write 1, and 3 we don't have 3, so this will give the same. Now the next is this one, 1 2 3. Here 1 is going to 2, so 1 is going to 2 we can write, and 2 is going to 3, so 2 is going to 3, and here 3 is going back to 1, so 3 is 1. From here we'll multiply these two permutations, so 1 2 3. When we multiply two permutations, it always goes from left to right, so we will multiply from left to right. We will start from left, so here we will start from 1 goes to 2 here, and this goes back to 2 here, and we will start from 2 here, so 2 goes to 1, so 1 is going back to 1. Now 1 is done. Now we will go for 2 is going to 3, and this 3 is referring to 3 here, so we will start from 3 is going to 3, so actually 2 is going to 3, so we will write 3, and 1 is going to 3 is going to 1, so we will refer this 1 to this side, and we will start from 1 here, so 1 is going to 2, so actually 3 is referring to 2, so we will write 2. Now here the product of these two permutation is given as this. Here we can cancel this 1 and 1. So we can write 2, 3 or 3, 2. So we will take this 2, 3. So the answer is 2, 3. Similarly, we can multiply this. If we multiply 1, 2, 1, 2, 3, then same thing. We will get 1 is going to 2. So 2 is going to 1. So 2 is going to 1. 3 will be same. Again, 1, 2, 3. We will find for this one. 1 is going to 3. So 1 will go to 3. And 3 is going to 2. So 3 is going to 2. And 2 is going back to 1. So 2 is going back to 1. Now we will multiply these two. 1, 2, 3. So we will multiply, and we know that when we multiply two permutation, we will go from left to right, and we will start from 1. We can start at any point, but I'll start from 1. So 1 is going back to 3. Here 3 will start from 3. So 3 is going back to 3. So 1 is actually 3. Now next is 2 is going to 1. And here 1 is going to 2. So in place 2 is actually going to 2. So we can write 2. Now 3 is going to 2. And here 2 is going to 1. So 3 is going to 1 actually. So here we can cancel 2, 2 since they are same. So we can write 1, 3, 1, 3. The final answer is 1, 3 or 3, 1, but I will write 3, 1, 3. The answer is 1, 3. Similarly, if we multiply the next 1, 3 to h, then the product of this one will give us 1, 2, and this one will give us 2, 3. Similarly, if with 2, 3, with 2, 3 and 1, 2, 3, we will get 1, 3. 2, 3 with 1, 3, 2, we will get 1, 2. And 1, 2, 3 with 1, 2, 3 will give identity. 1, 2, 3, 1, 3, 2 will give us this. Now the next question is, let H be a subgroup of a group G such that there are exactly 2 left cosets of H in G. Then prove that every left coset of H in G is a right coset. Is a right coset in G and vice versa. So since AH is a left coset, it is given that there is only one more left coset of H in G, that is AH. Then AH is not equal to H, and A does not belong to H. Now AH intersection H is empty, and AH union is G. AH union H is G, and hence AH and H are complements to each other in G. That is, if G minus H is equal to, will give us AH, and XH equal to AH for all X does not belong to H. Now if X belongs to H, then HX equal to H or HE equal to H. On the other hand, for any X does not belong to H, and HX equal to H inverse X, X inverse H whole inverse equal to AH inverse, and H inverse A inverse will give HA inverse, which will give HA. Thus, HA and H are only right cosets of H in G, and hence HA is equal to G minus H is equal to AH.